Well, I don't know where you are all sitting today. Of course, most of us are inside, but it's so windy out where I am that I almost need a seatbelt even inside. But I trust you're having a good day. So my clock just rolled over to 12:30, so let's go ahead and get started. Really appreciate you attending again today, the Data-Driven Agriculture webinar series. We're really talking about the possibilities of today and the potentials of tomorrow. In the series, we're covering lots of different topics, including forest management, which is the topic of today, but on different weeks, things related to cropping and livestock, produce safety, and disease outbreaks and things like that. Next slide. So this series is sponsored, of course, by Purdue Agriculture. You can tell that from the color scheme and the logo there. But we do have some resource sites there for you to access at your leisure. The Digital Ag Resources website, a specific site related to UAVs and extension. And then much of this series, not necessarily today, but much of the series is sponsored by the Wabash Heartland Innovation Network, which was a Lilly Endowment gift to a 10-county region. So these are the topics coming up after today. We certainly invite and encourage you to attend as many of these as fit your schedule, always Thursday, 12:30. They are all recorded. Excuse me, we're just a little bit behind in putting the last couple webinars up on YouTube, but as posted, registered for this series, you will get a reminder of the links to those postings on YouTube. And so feel free to forward if you realize after attending today, well, I wish so-and-so could have participated and seen that. Well, good news, they can participate and see that. You just give it to them after the fact. So watch for those announcements, and these are the ones going forward. So we do encourage you in particular to use chat extensively. So open the chat box, pose your questions there. Our presenters will respond, perhaps in chat. Maybe we'll do it at the end via Q&A. So we would ask that you just keep your microphones muted and your webcams off, at least until the end, and then probably we will have some time for some live Q&A. We'll probably first address the questions that are in chat, and then just have a good conversation among the rest of us. So do use chat. We encourage you to post resources, pose questions, and things like that. So without further ado, Songlin, go ahead and share your screen, and I'll just briefly introduce our presenters today. First up is Songlin Fei. He is a professor of forestry and natural resources. He's also the Dean's Chair for Remote Sensing here in Purdue Agriculture. He directs the integrated Digital Forestry initiative, which he's going to talk about here a little bit, and specifically regarding forest inventories. Right after Songlin presents Joe Hupy, who is associate professor in aviation technology and transportation. He's also, by courtesy, has an appointment in forestry and natural resources and earth, atmospheric and planetary sciences. Joe will be talking about procedures and the benefits of remote sensing, sort of the tech involved in doing some of this work. And then following Joe will be Dr. Jinha Jung, who is assistant professor in civil engineering, and he'll talk specifically about light detection and ranging and data sets and how we can use those in ag and forestry applications. So before I just let Songlin go and present, I would just like to point out that this is a wonderful example. 3 professors from 3 different departments, actually different colleges, working together to solve challenging problems in agriculture broadly defined. So I really do hope you'll enjoy today's presentation. And Songlin, Joe, and Jinha, thanks very much for presenting. Please go ahead. Thanks very much.
All right, well, thank you, Dennis, for the great introduction, and thanks everyone for participating in this digital forestry presentations. So I want to give you a brief background about this digital forestry initiative. This is a grassroots effort across the campus in the mission of trying to, in general, overhaul forestry from the, traditional tape and stick measures, to promote it utilizing those digital technologies to bring us to the digital age. And so again, this is a grassroots effort, and we have currently about, well, counting on the screen, we have 16 faculty members through different groups working on this together. And it's an open group. So for folks that who are on campus and wanted to, work with us on bring your talent onto this group, feel free to contact me, and I will be happy to enjoy to have you all to work with us. And for those of you are not on the campus, we're always looking for potential partnerships, working with you to solving whatever the problem that you have on the table that you think we can bring some solutions to you. And so with that, I'm going to, as Dennis mentioned, that we will have 3 talks today about the digital forestry. I don't know if you were presented in the 2 weeks ago with our first talk about the Digital Forestry Initiative. That was primary focus on the terrestrial systems. So if you missed that, I think Dennis mentioned that the YouTube links will be available to us soon. But today we'll be primarily focusing on the aerial systems. And so we have 3 brief presentations. Mine will be a brief overview of the opportunities and challenges for the aerial forest inventory, and followed up by Dr. Hupy and Dr. Jung on some of the more specifics about operations and resources. So to begin with, I want to point out that Indiana, as a state, we are somehow lucky in terms of having a lot of great geospatial data. And one of this is an aerial inventory. So the state of Indiana by now, we have 2 complete manned aircraft resulted LiDAR data. And these are what we classify them as the medium resolution LiDAR data. And these are wall-to-wall coverage for the entire state. Now, originally, they're not necessarily designed for the purpose of forest inventory, but they do produce a beautiful LiDAR density cloud that allows us to do a lot of that. And Jinha will give you more detail about the tools available and the data, where the data set in a second. But what I'm going to show you is that how in a way in forestry we can utilize this kind of information. And so on this graph over here, these are actually the data that rendered from these LiDAR data that was medium resolution. So what I'm showing here is an example of how we potentially could utilize this data set to do forest inventory. On the left of the screen is an area view of a red oak plantation, and this plantation is about 50-some years old. And on the right is actually the LiDAR products that I just mentioned. And here is that if you utilize certain algorithms, you can see that potentially each of these clusters of these color are representing an individual tree. So actually, if you do utilize this, applying some of the AI algorithm, machine learning algorithm to this data cloud, actually here's what you can do. So here's some results that showing how these data, in terms of measured from LiDAR, for example, on the left is a height estimation from this LiDAR cloud in terms of height measurement for individual tree, and versus what is the field observed height. And what you're seeing is that actually we're not doing a bad job. We have on the accuracy about 80% of the variability explained, and ISME within 3 meters. And you can utilize this data, also can infer in terms of, if you delineate the crown, you can infer what is the diameter of these trees that potentially look like. And the diameter is a little bit still coarse in terms of using the LiDAR data to infer that. I remember this is, again, a data product that is not designed for a tree inventory and detection. This has the data is have about 2 LiDAR returns, or maybe close to 3 LiDAR point returns per square meter. And the limitation that we are facing here is this: is that the current the example that I'm providing to you is only on the plantation, which means they have relatively uniform structures, and the layout of these stand is relatively regular. So the question is, what about this natural forest, right? And these are the majority of the forests that is ongoing and existing in the States, or in general, the other regions as well. And so lately we have been experimenting something that a more customized version of it. And this is a platform that built by Dr. Habib's lab, that equipped with LiDAR and other sensors on this platform. I'm going to show you in a video of what this system is capable to do. So as I don't know exactly how your system going to look like, but maybe the internet is not making the decent view. But just give it a second, and I'll show what this is. But what you're seeing is that with this LiDAR system, what you can see is that we actually this is in the natural forest. On the ground, you are seeing these downly woody debris and some of these shrub systems. And on screen right now, you can see the little blob of the green on that right side is the cars we parked over there. And then here again, looking inside is each individual stems, we can measure them. So what does that mean? Well, that represents a couple of interesting potentials here. Basically, what this tells you is that we can nearly do a complete forest inventory if we are interested in learning the how many board feet or volumes do we have in that stand, right? And so you can see size of the tree, distributions of the tree, and the other thing that is have a great potential that we yet to explore is that something that normally not come to the eyes of a forester or logger, but the things that are on the ground, which is the downed woody debris. And what that means is these are actually, you think about it annually, we always hear in the news about the wildfires happening in the West, and we have more of this stuff actually accumulating in the eastern forest as well. So these are fuels for the wildfires. And if we can do a decent job of mapping and locating where are the high-risk areas, this could have tremendous implications in terms of moving a step ahead of where the wildfires are happening. And again, this is some ongoing work that with the aerial system that is more of more work that need to be done in terms of the more specific feature extraction. I'm going to quickly also mention some opportunities available here now is that, in addition to the LiDAR, which is a little bit too expensive to add ordinary users, we can also utilize something called the photogrammetry-based approach, which is basically an RGB camera, and you can mount it on these different platforms. And Joe going to give you an idea about what are the different platforms can do what specific things. But here's another example of how we utilize these UAS images with photogrammetry to delineate trees. So here are a couple of sites that showing on the left is the plantation at the Martell Forest. These are red oak plantations and black walnut plantations. Here's some preliminary results that we are about to submit. Is this that in general, what you can see is that we are doing a decent job of measuring the metrics in terms of the individual stems in the ground, on the ground measure, and the LiDAR measurements. And this is both in terms of the height measurement, which is at the top, and the crown size measurement, which is at the bottom. With in general, there's about R square values depending on the metrics that we're using around 80%, 70 to 80%. Some of them even better. So which means that if these are some of the key attributes that interesting to a lot of the tree improvement folks or the field measurement, is that the basics about height measurement or the size measurement we can do with photogrammetry using US-based overall area photos. Now, again, this limitation that what we have been experimenting here is primary in what the keyword here is plantations. What about the natural forest? Well, and this is another new area that we have been working with Jinha's group on this. And so here's a quick video of showing this is in something, if you are on campus, you should be able to recognize this. This is McCormick Woods at north of the campus by the golf course. And what you're seeing here is that this is actually a day right after the big snow that we have. That there's a lot of snow on the ground, but with this RGB photo derived 3D cloud, what you can see is that we actually can, stem mapping every single tree, and we can estimating the diameter and the height of the merchantable materials on this. And this has a lot of potential implications for the landowners who doesn't have the more fancy equipment, such as the LiDAR system that we mentioned earlier, but with an RGB system. What we're hoping for is that we can develop a system that you can dump your RGB data, orthomosaic RGB data to our platform, and we help you to automatically extract this information to make, allow you to make decisions right over there. So that's a brief overview about what the capacity that this digital forestry group is doing in terms of using the aerial systems. I'm going to stop sharing, and I'll let Joe to give you more specifics about the operation side.
Perfect, thank you. I'll just go ahead and turn on my camera, and I will share my screen. Thank you for that introduction and for that segue. What I'm going to be bringing up to everyone is more so the operational and the technological considerations for using UAS as a remote sensing tool. A lot of what I learned about UAS from the early days, going back to about 2011, was when I was using UAS much more in open environments. So when I first started using UAS, it was out of necessity because it was looking at areas that were very much devoid of trees, and I was looking at mapping out craters from explosive munitions. And then that led to me doing a lot of work in mining environments. And doing that work in mining environments, I more or less kind of had an idea of how to use UAS in a very different type of surface and I guess you could say reflectance than what you have with forestry. And a lot of what I learned with using UAS in forestry is really, it's almost turned upside down on its head, everything that I knew before. And a lot of the different tools and techniques that I use doesn't necessarily always have to be involved with mapping. If you look at this screen, you can see how there's a series of dots on those lower photos. This is where in forestry operations, sometimes if you just want to do scouting and stuff, and one option is just to use spatial video. Another thing I would say is that if you look over on the left side of this screen, one thing I'm going to talk about here in terms of operations is that what I've really come around to, especially in an aviation program, is that when you engage in UAS operations, it very much is an aircraft operation, and it's not just about getting the data. And in fact, if you treat this operation like an aircraft operation where you have checklists and standard procedures, and you maintain your equipment and you have that equipment connected, something like Measure Ground Control, which keeps track of all your flight hours, you can do mission planning, you can fly through it. It really makes for a much more streamlined operation. So I'm going to be talking about that a little bit today here as well. When we look at UAS as a remote sensing tool, there's a lot of advantages with UAS. And if we look at UAS from the beginnings, UAS was in many ways touted as this means to replace manned aircraft, especially in agriculture. Of course, anyone who's involved in agriculture outside of test plots and whatnot will tell you that there's this big issue called the wind, especially when we are looking at places like the western landscapes with a small farm covering 640 acres. There's a lot more to UAS than what was once touted. And in fact, if we start looking at things like satellite imagery with Planet Labs and stuff, we really want to think about UAS as a niche tool. That said, the advantage of UAS is that they can be rapidly deployed. This remains an advantage because even with Planet Labs and their toaster box size satellites that image the planet every day, when we start looking at the need to potentially go out and image an area right before a controlled burn or something like a harvest event in forestry operations and natural resource operations, being able to get that platform out that morning and engage in a mapping operation still has a great deal of value. They can be frequently deployed. They're very nimble and agile in terms of being able to fly in some tight spaces. This is very conducive in forestry operations. Of course, you can get a really high pixel resolution or ground space distance from UAS. The ability for them to fly that low means that you can engage in phenotyping of trees and whatnot. That high temporal resolution allows you to look at changes over time. And you can have high locational accuracy. One of the questions posed was, how do you get that locational accuracy? I'll talk about that a little bit here. There's a couple of different ways of getting control. And of course, you have a low operating cost. Now, I put an asterisk after that because one of the issues that you often saw, especially in the early days of UAS, was a lot of companies, especially mining companies and utility companies and whatnot, would say, well, we're going to do this UAS thing. And then they would stick the college intern on it, and then the college intern would crash the platform, or they would get this materials, and then they had no idea what to do with it. Disadvantages with UAS, a lot of these are related to what I will say, the FAA and their restrictions. One thing that I would always say in terms of starting up a UAS operation is they're investing in either someone with legal experience or the ability to write waivers is no small investment, but it's well worth it, because what can really put your organization ahead is the ability to get the waivers to be able to fly higher than the restricted altitude of 122 meters, but also to be able to fly beyond line of sight. Now it's fairly easy to get a waiver to fly at night. So if you're doing thermal operations, this is an advantage. But you also have a lot of weather condition limitations. What I always say to people is that when you're flying UAS, the issue is often not the rain or the heat or the cold, it's the wind. That's the number one reason why flights get grounded. And it's not just getting grounded out of safety issues. A flight can easily be ruined in terms of data collection, especially in a forestry operation, when you have the wind jiggling the leaves on the trees. Because then when you get into that photogrammetry that Dr. Fei mentioned, it doesn't have the tie points that are needed. You have altitude restrictions, you have airspace restrictions, can't fly over people, you cannot fly at night. You have data storage issues, you have data processing issues, and you have a high operating cost, because when you start looking at this in terms of the UAS operation itself, one thing to keep in mind is that you do need to store high amounts of data. You do need to process that data, and engaging in this data processing outside of even doing the GIS analytics in terms of image classification and whatnot, it requires some strong computing power. And you do have to start thinking about things like insurance and whatnot. These are all things that are easily overlooked, but when you start getting into having an actual UAS company and you start looking at all the overhead of maintaining this stuff, it does start to add up. And so it's something to consider in terms of what approach are you going to do in terms of how big are you going to go in terms of starting up this operation. These are some key factors to consider in UAS operations. What I'll say in this regard is that when you're looking at an aircraft in UAS operations, you really have two choices. You have the choice of a multi-rotor, or kind of like a helicopter type platform. This is one that we're most familiar with. When you see the media coverage, they often will show a DJI Phantom or maybe a Hexarota rotorcopter. These are great platforms because they're very stable. You can take off in fairly tight areas, but they don't have the longevity in terms of flight time that a fixed wing has. So if you're looking at forestry operations, oftentimes getting a fixed wing aircraft is going to be able to cover the larger areas. That said, one of the issues that you have is that even if I could put my fixed wing aircraft up for 2.5, 3 hours, I have to fly that within line of sight. And unless I have a waiver for both line of sight and altitude, I'm going to basically be limited to flying. If I'm at Martel because I have 100-foot trees, I could put that thing up to 500 feet and be okay, but I still have to be within line of sight. So one thing when I'm working with the forestry folks and everything, and they want to map all Martel, it's one of the things that I'm often saying is that it's not technological limitations that are holding me back from doing Martel in one whole flight. It's the legal restrictions. When you select a sensor in UAS operations, it was mentioned before that you can do photogrammetry with RGB imagery, but you can also engage in photogrammetry with multi-spec imagery. Sensors such as the MicaSense Red Edge or the MicaSense Ultim, which was actually developed to be able to fly in a manned aircraft at much higher elevations with its higher pixel resolution, are great multispectral sensors. But just know that when you're flying a multispectral sensor such as the Red Edge or the Ultim, they have a very narrow field of view. So your flight lines are going to be very, very close together. And if you're flying that with a fixed wing, that means that you're going to have to account for the turn radius of that aircraft. So these are just all little things to consider. Of course, thermal, the Ultima has a thermal band on it. I'm going to show you a mosaic that I created from that. And of course, we talked about LiDAR. I'm going to not talk about too much with LiDAR here. I'm going to focus more on the imagery side of things. A question that was asked before was with ground control and precision. How do you get the precision of location with this? In the past, when I used to do work in the mining sector and in the excavation sector, this wasn't too bad. But even then, the largest component of me doing these flights was me engaged in the survey. For me to do even a fairly small operation was about 2 hours of survey work. I was using a dual frequency survey grade GPS and going over and getting a point over about 10, 12 ground control points, and then doing a check shot on those as well. When we look at something now with something like the arrow point adds to the ability to just walk around and lay down these points, and they'll engage in fixed data collection over the period of time it takes you to do the flight with a minimum of 45 minutes. But the issue with forestry is that even if you look at these images over on the side here, if you have a ground control point down in the bottom of that heavily canopied area, you're not going to be able to see it when you go through and process the imagery, let alone you're going to have so much scatter of the GPS signal coming down that you're not going to have a very good point in terms of RMS error and locational accuracy. So one way around that I'm really excited about, that I tend to use a lot of these days, and all the platforms that I develop for anything with research related or advanced classwork has PPK technology. And PPK is it's post-processing kinematic. And what that does is after your flight is over, you have the ability to take that GPS log on there, the rover log, and you can tie it into a fixed point on the ground. Oftentimes this is, especially in a place like Indiana when we're so close, you would tie it into the Coors network or continuously operating reference station network. And that allows you to get the precision that you want without the need to have all those control points. Another one talked about quite a bit is RTK. RTK is PPK, but it does it on the fly in real time. The issue with that in forestry, though, is that if you lose connection with the platform, let's say because of canopy and whatnot, your RTK signal is destroyed, and therefore your accuracy is destroyed. So it's something that I just tend to shy away from. Although RTK is definitely, I mean, it's a great form of correction if you have an open view with your ground station and your platform. Now, moving into some of the stuff that I have over here, this is some stuff that I'm actually writing a paper right now on best practices. When we start looking at these operations, one thing to really take into account is a safety management system. Before you even do anything, what you really want to do is you want to get a safety management system in place in terms of what happens if something goes bad in the flight. What do you do? And you want to train on this. If you lose GPS on your platform, what do you do? What are the first what are the first measures that you take? What are the secondary measures? What do you do in an extreme situation? And this is something I learned the hard way over the years after having several incidences that did go bad or almost went really bad, is that having this in place is really integral. Just like crew resource management. Crew resource management is more or less everyone on that flight crew who's engaged in the operation, understanding their role and following that role in operations. And what I'm showing you over here is that this is two different images. The left side is in focus. The right side is out of focus. The reason why it's out of focus is because somebody on the flight crew didn't follow the checklist and engage in setting that lens to infinity focus. They just assumed it was set to that because it always is, but it probably got bumped and whatnot. And you have a data set that, yeah, it was a safe mission, but now we have a data set that's useless because people didn't follow their roles. And that gets into checklists. Following a checklist is very important, and having a standard operating procedure is important because that standard operating procedure is what we really need to have it where we can go out and we can gather data in the right way and consistently. If we look at this, we have some blurring from windy conditions because somebody flew during windy conditions, just more or less going out there to get it done and flying. And then we have shadows. And the shadows are from flying too early in the day. And in other operations, this isn't a big deal, but when we start looking at forestry applications, having those shadows is a problem. For platform comparison, when we start looking at multi-rotor versus fixed wing, we can see that you have advantages and disadvantages of both. What I'll say is that with multi-rotor, their advantage is that they're much more nimble, but what you also have to take into account is that they have a shorter flight time and you have higher demands in terms of cost and what you have to do to replace those batteries. Multi-rotors are beneficial for smaller areas, less experienced flight crews, smaller flight crews, tight takeoff, landing. Fixed wing, pretty much the opposite of that, to where they have longer flight times, but you have a few more requirements. If you look over on the right side, you can see a catapult for launching a fixed wing. You can see the sensor payload on the bottom of that. And you can see the parachute bay right here to where that parachute is loaded. Now, why does ground control matter? Ground control matters because you have to establish that control for you to get the precision and location. And you need that precision and location when you start dealing with these temporal operations in UAS with forestry, when you start laying one data set on top of another, or when you start doing things like modeling canopy height, because that vertical control is going to be important. Like I mentioned before, I'm a big fan of PPK. And the reason why is because I can have it where I can have control and I don't have to worry about a ground control network that I survey on the ground that, for one, I wouldn't be able to see if it's in the canopy, but also the quality of that signal is diminished. For UAS to be successful, you have to follow 3 rules. You have to be able to fly it low, you have to be able to fly it slow, and you have to fly under control. Now that is a safety standard, but it also means you have to be accurate and timely. And if we start looking at using UAS in environments where they really are useful, you really want to have the ability to not have to wander around and put out control. If you look over on this far right image, this is before PPK was widely prevalent, and I was mapping out a naval weapons range in California. And I had to go out and I had to be aware of things like unexploded ordnance and even minefields when I put out these control points. So, you know, we're sitting there and we're saying there's got to be a better way to do this. If you look over here, this is McCormick. You can see how we have our GCPs all along the outside, which is really distorting our data. And then the inside, we don't have any GCPs, and we even have a void in terms of being able to process because we couldn't tie that in. So with PPK and RTK, especially PPK, we have the ability to get that precision without that problem. We look at this in terms of natural resource management examples. This is an example of how we can use that PPK technology to where, in this case, we had a controlled burn. Before that controlled burn, we were able to get out there, we were able to get in a flight of very nice high resolution imagery using a MicaSense Ultim sensor. And then we were able to fly that area immediately after. And then using classification techniques, we were able to look at the ground cover in terms of what was burned and what was not. This is something that I have in ESRI Story Map. I'm not going to go through the map, but in this ESRI Story Map, I go through and I more or less tell the story of the burn. And I have some false color IR imagery where people can scroll before and after the burn to compare. I have an NDVI index where you can look at before and after. And then I have a thermal of before and after. This is all from the MicaSense Ultim. And you can zoom in and out on these interactive maps if you wish. So it's a pretty nice story map to kind of get an idea of how you can use that multispectral imagery, in this case in natural resource management. And finally, this is a temporal series. One of the things I was talking about before was how you can have a temporal series of data surveys. In this case, what we were able to do is we were able to take advantage of the high temporal abilities and the high spatial resolution abilities of this sensor. And we were able to fly this burn plot before, during, and immediately after, and then several other dates after, to get a great time series of how, in this case with this burn disturbance, how that area revegetated and what it revegetated with. And you can imagine how this can relate to other types of forms of natural resource management or in the realm of agriculture or forestry in terms of harvest events and whatnot, how we can use this, the capabilities of UAS with that niche ability to fill the void between satellites and manned aircraft to do this. So I'm going to stop here, and I will be more than happy to take advantage of answering any chat questions, and I'm going to turn it over.
Thank you, Dr. Hupy. My name is Jinha Jung. I'm going to be talking about Indiana statewide LiDAR data and its application. And before I start, I want to acknowledge my co-authors for this presentation because without their support, all of this work is not going to be possible. And I have Dr. O and Joshua, he's a postdoc in my research group, and Joshua is a PhD student Dr. Fei, Dr. Xiao, Dr. Kong and Xiao, and they are in the FNR and also in the Purdue Library as well. Like Dr. Buckmaster mentioned, this is a truly I'm going to call it a transdisciplinary, the collaboration that made it possible. So, it has been mentioned by Dr. Fei earlier, Indiana has been one of the state where we've been collecting statewide LiDAR data periodically, and a lot of people actually don't know how much of money that has been invested to make this happen. And actually, this in the first round, which was acquired from 2011-13, it was about $4.6 million investment from the USGS and USDA to make this happen. And in total, turned out to be about 11 terabyte of data. And more recent data collection, which was about a $6.6 million investment to make this happen. And they happen to be about 13 terabyte of data being collected out of two statewide LiDAR data collection cycle. And if you just add these two numbers, it is over $11 million investment that has been put in to collect this kind of data set. But when I first arrived here at Purdue, the understanding how this kind of data set is being distributed, I saw that there is some great opportunity over there. For me to contribute. So the way how it works is once those vendors collect the data, they're going to put all those data set into external hard drive and ship it to the Indianapolis office. Then this is going to mail to other location where they need the data, and another location, and that happened to be mailed to Purdue University. And I volunteer that I can just host those kind of data sets so that people doesn't need to wait until this drive is mailed to their location and they start to use the data set. So if you look at the overall process of LiDAR data set, how this is being generated, including airborne images as well. We have raw images being collected with GPS INS and range measurements and optical images that need to be processed to generate the 3-point cloud and orthomosaic for the aerial images. Then for the most recent data collection, vendors is going to do the point cloud classification so that we can generate something called the digital terrain model, which is in elevation of the ground. That is pretty much it. We're going to be receiving these two data product as part of it. But if you look at this in a LiDAR technology, and there is a lot more that we can actually generate out of this one. The one of the example that you're seeing at the bottom is the DTM that we're looking at. And of course, we can also something called the digital surface model, which is an elevation of the high surface around this, the transect over here. We can generate the surface model as well. But if you look at this DSM minus DTM, which is essentially height above ground, that we call that as an NDHM, which is normalized difference height model, can be also generated. So what I did after I received those data set from the state initially, which only had the point cloud and DTM, I went ahead and generated the surface model and NDHM. And now, how we're going to be actually hosting this kind of data set to the public. I don't want to be kind of shipping out this data set to other people by mail because it's going to take time, and sometimes it can be damaged during those the shipping process and as well. So what my research group ended up doing is actually developing a website that you can have an access to all those data set and the additional data product that has been generated. So what I'm going to do now is that I'm going to actually visit this in a website, which is URL is over here, lidar.jinha.org, and this is open to public, so anybody should have an access to this. So if you just go to this website there, just click, and you're going to have a pop-up window that talks about who actually contributed the money funding to make this happen. There are additional links that you can follow, and I know that there is one question in the chat window: what is the accuracy of this LiDAR data set? If you just click this link here, we have have an elevation accuracy assessment done as a part of this data acquisition process. So you can just open that up. They have some actual evaluation and assessment numbers included over here. The non-vegetated area, we have about 10 centimeter root mean square error, and with a 95% confidence level, it's going to be about 20 centimeter for the open area, and this VVA is vegetated area is about 30 centimeter. 95% confidence height and elevation accuracy. And I'm gonna just close that out. You click OK, and if you just go in, there's nothing but just in a map. You can just zoom in and zoom out every time you just move your the cursor around. I like to go to the, the Multnomah County because, that's where we have, state listing over there. So once you just, move your mouse over the specific county and you just click it, and there's going to the top of window shows up, it says in the LiDAR data download. As you click it, and you're going to go down to that specific county that you just selected, and you're going to see that this tile structure, this is an actual tile that was delivered by vendors. So you can just zoom into a specific location that you are interested. For example, the IU campus, you just click here, then you should be able to see that different links where we can download the LiDAR data from 2011-13 cycle or 2018 cycle. For the 2008, 16 and 19 cycle, we have not only point cloud and DTM, but I also generated that we also generate the surface model and the NDHM as well, so they can download that. And another thing that you can do here on the website is, because downloading those data sets is going to take some time. So if you just want to see how those terrain model and the NDHM looks like, you can just click this button on the right, so they can see that this is a terrain model visualized on the fly for the whole county, so they can just zoom in. And you can also turn on this NDHM layer, so they can actually see the the canopy height model or the normalized height model visualized right away. And you can just turn this on, then you can specify down, click this one to download all those data sets to your local drive, so that you can further analyze those information if needed. And if you actually want to download those, for example, whole county data set, you don't want to click through, all those, tiles to download them all. So what we did was, we also created another directory where you can have an access to, the county in a directory structure. So all you need to do is an IN 2019 at the end of this URL. Then you're going to see this kind of, the directory structure over there. For example, if I go to Multnomah County again, if you just click this one, then you're going to actually move into that specific directory. Then you're going to see that DSM, which is service model, DTM is terrain model, LAS, which is LiDAR point cloud data, and DHM NOP is a number of point that is used to generate the all these additional data product. But not only that, you have also county mosaic generated from for these service model and DHM as well. So you can just directly download those in the whole county in this way. So coming back to this, the presentation again, this was in a live demo of this website. It's open to public, so anybody can actually go to download the Indiana statewide LiDAR data for your research. And so this kind of data is good, but what's the good use of this kind of data set? So one of the most recent effort that we are developing together is trying to come up with some kind of tree height measurement evaluation or an assessment, not at the smaller scale, but much larger area. So what we are looking at here is trying to use CFI, which is continuous forest inventory data that has been collected for the whole Indiana state. It has collected twice, 2019, 10, and 14 and 15. Total of over 6,000 plot we have in a height measurement, and the area that actually this being collected is about 20-foot radius. And we also do have Indiana statewide LiDAR data, which is collected almost not exactly the same year, but kind of few years apart. But the key thing here is about the 5-year part between these two data collection. So you can just see that for each plot we have a height measurement over there. So what you're trying to do here is that we want to see how much of the growth that we have just looking at the CFI data. This is X is CFI data collected in 2019 and 10, Y is in 2015 and 14. We're going to see this kind of trend, and we just look at the same plot using the LiDAR data. You can see that this fit is much tighter. And if you look at some of this example over here, we can know that the tree is not going to be getting shorter, unless it is harvested or has some kind of the management and operation done in the field. You can see that most of the the plot point here in the LiDAR is over this one-to-one line, which means that it is somehow growing, but that there is some uncertainty involved in this CFM measurement, which kind of give us a kind of confidence that this kind of LiDAR measurement might be actually doing height measurement better than the manual measurement on the field. And when we actually apply this one to the the example that we saw earlier here is Yellow State Forest where we actually ran out, did a survey with, survey grade GPS for those CFI plot and, compare those two locations. But when you actually expanded the same scenario for the whole state with over 6,000 plot, this is what we see, which is a pretty similar trend. And especially if you look at this, taller trees, there's a lot of, deviation for the manual measurement over here versus, LiDAR kind of, converges in a much, tighter, which kind of might be another indication that the LiDAR height measurement might be much more consistent than the manual measurement. Current ongoing project right now, because of this, we want to actually assess the, the accuracy of height measurement from statewide LiDAR data, but establishing correspondence between actual manual measurement versus actual LiDAR data is very challenging because when we actually survey the CFI location in the field, it's under the canopy. It's not based on survey grade GPS, so there's a lot of uncertainty over there. So we are trying to do right now is can you actually collect the data in leaf off season so that we can actually collect we can actually evaluate the accuracy of this height measurement much more accurately. So we collected data with recent the latest platform, Matrix 300 with RTK with the GEMIS P1 system, which has a 45 megapixel and RGB camera, and they generate 3D point cloud, auto mosaic, and the different data product. So this is the UAV data collection. And we also visited the same location with a field crew. So we are collecting all this information and also doing a GPS surveying with the tunable R10 GPS. Because this surveying is done in the leaf off season, we are expecting that this position and accuracy for the location we're getting ground measurement is going to be much more accurate. So if you look at this data product, this is the actual 3D point cloud that is being generated from this P1 platform. And this is the auto mosaic that is being generated. All those orange dot is the location where we actually collected the ground measurement. If you zoom in, you're going to see that this is the survey location. We have a height measurement, DBH, and the diameter of the trunk, and what is the height to the first branches. All sort of different information is being collected right now, and we are in the process of trying to extract similar information from UAV data set. So with that, I'm going to end my presentation and give my back to the Dr. Buckmaster.
Okay, well, Songlin, please turn your webcams and mics back on too. We're open to any Q&A with whoever's attending today. We invite you to post some questions. Maybe you three presenters can sort of rescan if you didn't lately chat. If there's any, maybe we start there. If there's something to add to some of the Q&A that's already there, feel free to do that. I did, just to give you time to think about it, I was thinking, Jinha, when you were presenting, I heard about two students who went to your site to get the topography data, the LiDAR data. The one went to Bloomington and all they found was a deep hole. And the other student went to West Lafayette and they found a mountain.
Yeah, I mean, the fieldwork is always challenging and we never know what is out there, and that's exactly what we're learning as well. And when you a lot of my research group has been focusing on the research plot data collection, but when we actually first went out to Glenwood, which is East Indiana, we flew the data, and we are not able to actually process because it was actually very cold, and we are not prepared for that that kind of cold weather. So Josh and Sun, we are wearing almost like in a very thinnest clothes that we can have, and we are almost having a freezing temperature out there. So I mean, the field work is hard, and that's what I just want to mention.
So any three of you feel free to sort of take the mic and run. If someone wants to unmute and pose a question, you're open to do that. Go ahead.
Well, one thing I want to testify here is that I'm not a U.S. pilot, and when I just learned about the technology about using these different tools, I was super excited. But on the other hand, I also was quite naive in terms of thinking always just take a couple of pictures from the air, right? Well, the reality is way more challenging than what you think. So this is what Dr. Hupy was mentioning about. If you don't do these general procedures, you might come back with a bunch of images, but it's not necessarily useful one. And the key is how can you stitch them together and make them a useful information. So I would highly recommend, if you I know that Dr. Hupy's group is publishing one paper about the PPK procedure, and he's soon publishing another manual for forestry-related data acquisition. So take a look at those.
Yeah, I also want to echo that. And I used to say there's a lot of people who knows how to fly UAVs, but there's very little who knows how to collect the data using UAVs. So there's two different things, the knowing how to fly and knowing how to collect the data. That is two different things out there.
Yeah, I mean, it's an ongoing process, and I really do think that we're, in terms of UAS data collection, we're pushing the frontiers of UAS. And outside of what we're talking about today, I mean, one of the big things that I'm really excited about with UAS is how they can integrate into IoT. And when we start looking at how UAS can have more than just imagery sensors on it, we start looking at atmospheric sensors and sniffers, if you would, connecting to a ground-based network. We start looking at how we can use edge-based computing on these platforms. We're really going to start pushing the limit in terms of what these things can do. But I mean, what I'll say over and over again is that I came into UAS from a background of soil geomorphology. I was soil geomorphology, a little forest ecology. I looked at how battlefields recover from explosive munitions. And the way that I got into UAS, fortunately, was I was trained by people who were big into the operations. But over and over again, I can't stress enough to where the good data comes from the people that have that entire checklist and SOP, everything. I mean, little things such as if there's, I think that there's one former student here, Jasper Sadi Klein, who's probably rolling his eyes at me, but I get apoplectic when an SD card is not put back into the same spot. If somebody removes an SD card and then doesn't put it back into the sensor again, or doesn't put that SD card in its hard case and into the same exact slot in that case as it goes, I freak out. And students roll their eyes at me. And I say, the reason why I'm doing this is that, how would you like to be out in the field and have it where you go to get that SD card and it's not there? Well, guess what's happened to me and to other students is that exact same thing. Or I had a student who didn't return the SD card to the hard case, and then they were opening an office door and their SD card full of all their data from their mission cracked in his hand. Just little things like that. I mean, SD card, it sounds so weird, but it's all part of that SOP.
Another plug that I want to mention here is that you saw me demonstrated the LiDAR data from Dr. Habib's platform, and I think this will be a new revolution in terms of the large amount of data that will be coming into the forestry sector that allow us to do way different level of feature extractions.
Okay, we're close to time here, so I just want to make sure, Joe, Jinha, Songlin, any parting comments? Maybe I'll have Megan go back to our closing slide if you have anything to add there. Okay, well, we certainly do appreciate you participating today, and hopefully you've learned some things about I at least now have a better appreciation for standard operating procedures, and I understand why they exist. So thank you, Joe, for that. So these are the upcoming webinars. We certainly invite you to participate. And then certainly I want to extend a personal and institutional thank you to our three presenters, Songlin, Joe, Jinha. Thank you very much for just a very educational, inspiring, actually. When we look at what the potential is here, it really is tremendous, and we appreciate you sharing your work with us. So best wishes to all. If you go outside, make sure you hang on to all sides of your umbrella. It is sure to go upside down. Have a great day.
Thank you, Dennis.
Thank you.
Thank you.